Alright, so we're really starting to get into the meat of aerobic respiration now. We're moving on to the Krebs cycle. And just looking at where we've come from, we've finished glycolysis. We started the breakdown of glucose way out in the cytoplasm. We turned it into 2 molecules of pyruvate or pyruvic acid, and we've continued this breakdown of that original glucose molecule. We've continued destabilizing, continued ripping hydrogens off of it in the acetyl-CoA step, added a couple CoA molecules to it, lost some carbon dioxide, and now we have 2 acetyl-CoA molecules left over. That's 4 carbons left of the original 6 in our glucose molecule. We've also we've reduced some coenzymes along the way. We've reduced some NADs to make NADH to ship them down to the electron transport chain. We've made a couple ATP via substrate level phosphorylation, and we're going to get into the Krebs cycle now. Okay, so here we go. Let's look at the cycle itself. Recall that we're starting with acetyl-CoA. Okay. We're starting with 2 acetyl-CoA molecules, each of them 2 carbon molecules, and they're going to enter into the cycle up here in the upper left and react with oxaloacetate. Alright, oxaloacetate is a 4 carbon molecule, so let's keep track of our carbons. We have oxaloacetate, which is a 4 carbon molecule reacting with an acetyl-CoA. 4 plus 2, that's going to be 6 carbons. So we've made this citrate molecule. Citrate is the ionized form of citric acid. Sometimes you'll see this Krebs cycle called the citric acid cycle. It's named after Hans Krebs, the guy who discovered it, but sometimes it's called the citric acid cycle because citric acid is the first product of this cycle. So we have our 6 carbon molecule of citrate, which is once again the ionized form of citric acid. Citrate is going to get rearranged, okay, to isocitrate, an isomer, by the removal of a water molecule and the addition of another. So it kind of, the water input and output kind of balances itself out here in this step. So a lot of times it's not even included. But this is a reason why you need to stay hydrated for this initial step. So we're at isocitrate. We're going to have some coupled reactions moving on to the next step. We need to make our way from isocitrate, a 6 carbon molecule, to alpha ketoglutarate. And the coupled reactions are, one, we're going to have a decarboxylation. You see right here, carbon dioxide is going to leave. Also, at the same time, we're going to have a reduction event where NAD, the coenzyme NAD, is reduced to make NADH, and that NADH, as you guessed it, is going to take that energy to the electron transport chain to make ATP in that step. Alright, so now we've transitioned from isocitrate to alpha ketoglutarate. We lost a carbon, alright? We lost that waste product, CO2. You've exhaled it. Remember we lost the CO2 in the transition, the acetyl-CoA step. Now we're continuing to lose more here in the Krebs cycle. So we've gone from a 6 carbon isocitrate to a 5 carbon alpha ketoglutarate. Notice here we're going to have another decarboxylation event. CO2 is going to leave, coupled with the reduction of NAD once again to make NADH. At the very beginning, when acetyl-CoA came in, I probably should have mentioned this then, the CoA group right here leaves, alright? But it didn't go anywhere. It comes back in this step. And recall, why did we put the CoA on the acetate in the transition reaction or in the acetyl-CoA step? It was to destabilize it. Well, it comes back into play here, but it destabilizes the next product. So we're going from alpha ketoglutarate, we're losing a carbon, so we're going down to a 4 carbon succinyl-CoA. Okay? Sometimes you'll hear it called succinyl-CoA, succinyl-CoA, same thing. So we have the addition of a CoA, we have the reduction of NAD, and we have the loss of a carbon to transition from alpha ketoglutarate to succinyl-CoA. and it's unstable because of that coenzyme A. So quite quickly, the CoA leaves, and we have our first substrate level phosphorylation. All right. Here we're using guanine diphosphate. Okay, it's another nucleotide similar to ADP, but it's GDP. We're going to phosphorylate GDP to make GTP, which immediately then, in an immediate step, phosphorylates ADP to make adenosine triphosphate, once again through substrate level phosphorylation, because we're ripping a phosphate off of a substrate, in this case succinyl-CoA, to make ATP. So we've made one ATP so far, but remember this is eventually going to spin twice because we have two acetyl-CoA, so we're going to make two ATPs. But that dephosphorylation event changes succinyl-CoA to succinate, our next 4-carbon intermediate. We're going to have another reduction event. All right. This time we're going to reduce another coenzyme. Not NAD in this case. We're going to reduce FAD, flavin adenine dinucleotide. And we're going to rip 2 hydrogens off succinate, add them to FAD to make FADH2. And what do our coenzymes do? They're energy carriers. It's going to take that energy to the electron transport chain to help make ATP through chemiosmosis. When that happens, we've converted succinate to fumarate. All right? We're at the fumarate step. We're almost there. Looking back on all of these intermediates, just like glycolysis, these are all enzymatically affected steps. Okay? The initial reaction, or not the initial, but the conversion of citrate to isocitrate was an isomerase. Okay, you probably knew that. I probably don't need to go back through. The next step was a dehydrogenase because we're moving hydrogens. Same with the following one. Okay, when we made ATP, that was a kinase. The conversion of FAD to FADH, that reduction event, another dehydrogenase. Okay, so you get the idea. Same types of chemistry are going on, but just kind of a different venue and different chemicals. So we're at fumarate. Okay, we have to go from fumarate to malate. This is an enzyme called fumarase that speeds up this reaction, and we also need the addition of a water molecule. So when you're feeling dehydrated, if you're not getting enough water, this step is going to break down. All right, you're going to get a headache, you're going to get lightheaded. So if you're not feeling well and it's the morning before school and you have a headache because you're dehydrated, and tell your parents, Mom and Dad, my Krebs cycle is breaking down. I'm just not able to convert fumarate into malate. I'm having a tough time this morning. I need a glass of water. They'll get you a glass of water, get you up and running again. You'll have malate. All right, 4-carbon molecule. On our way back to the beginning of the Krebs cycle, we need one more reduction event. We're going to make one more NADH using a dehydrogenase once again. And then we're back to the beginning. We're back to oxaloacetate, and that's why it's a cycle. All right, we have regenerated our starting product. It can once again react with another acetyl-CoA, and this Krebs cycle can spin once again. Recall, let me repeat myself. For every glucose, there are 2 acetyl-CoA. All right, this Krebs cycle is going to spin twice for every glucose. Okay, because there are 2 acetyl-CoA that need to go in. So let's look at the inputs and outputs. First, let's look at the outputs. Okay, this is per 1 glucose, as I just said. So it's going to be 2 spins. In 1 spin, we lost 2 CO2. So in 2, we're going to lose 4. 1 glucose is going to make 6 NADH plus H's because it made 3 per spin. It made 1 FADH2 per spin. 2 spins means that it's going to make 2 of them. All right. That CoA is going to be floating around. It's going to be recycled. Here, all right, it left from our acetyl-CoA. It's going to go back and be used in the transition reaction. It's going to destabilize succinyl-CoA here. So this CoA is going to be floating around, and we're going to make 2 ATP per glucose. And this was an input. All of these inputs came as a result. And here's your waters. We need to put those waters in as well to stay hydrated to convert fumarate to malate, as you recall. All right, and obviously we needed to phosphorylate ADP in order to make ATP. So these outputs are extremely important. These coenzymes, we made them for our next step. You're going to see in the next screencast how important these are when we're talking about the electron transport chain and ATP production there. So, progress report. Where are we? We've gone through glycolysis and we made 2 ATP through substrate level phosphorylation. We reduced 4 NADs to make NADH plus H. We went through the acetyl-CoA step and we made 2 more NADHs that can travel to the electron transport chain. Now we're at the Krebs. 2 more ATP, 6 more NADH plus H's, 2 FADH2, all of these coenzymes moving on to our next step and the most important and the most productive step of aerobic respiration, the electron transport chain. So stay tuned. We're going to go through that and talk about how we make the rest, the vast abundance of ATP through respiration.